And for all the international fans out there who are watching this video, we just finished watching a small segment of Monument to a Dream, building of the St. Louis Arch. Yeah, one of my videos got banned in 5 countries. There's an international market out there causing all sorts of trouble with physics.
Why? What could you have possibly discussed that?
I think it was banned. I don't know for sure. All I see is that it's banned in, I think, Pakistan, and there were a couple others. Pakistan was the one I remember. Showing Tacoma Narrow's disaster, and so it could be just they didn't want. I don't think it was a copyright issue, because copyright has not gotten me banned before in those countries. I think it's perhaps because you show a bridge collapsing, they don't want that.
It might be like an auto detected thing like that. That video the original video might have been banned too, and then the system automatically detects that video is in your video. So
that why the original video would have been banned? Because it showed a bridge collapsing? All right, so I take this and I start bending it. Now, notice that when we're finding force divided by area here, when we're looking at this force divided by area, that's the original cross-sectional area that we're looking at. So my area starts dropping at this point because it starts to neck. And so it doesn't require as much force in order for it to break. But if instead I looked at the area at that point, as it necks, look at that cross-sectional area instead of my original cross-sectional area, that's also stress. The difference is, this is sometimes referred to as engineering stress. And the other one where you look at the area, so force divided by area, where this is the instantaneous area. As opposed to, I guess, the original area. This is known as true stress. Similar to strain, when we're dealing with strain, it is the change in length over the original length. This is engineering strain. But if you look at how much it stretches based upon the length that it is at that moment, we're now getting into a little bit of calculus. So this change in length is more instantaneous change, or an infinitesimal change, so it would be dl over L. And this is known as true strain, true strain. Or logarithmic strain. And what was the other? There was that's why I couldn't remember it. Somebody's name. Henke strain. Although I'll tend to refer to it as true strain. And it's basically, because once it stretches to a certain amount, it's not necessarily going to stretch the same amount under the same amount of force. And so it basically is looking at what is the change in length based upon the instantaneous length. The diagram looks a little bit different when you start bringing that into it. So if we put a little sub t for the true, it tends to look more like that. Now, a lot of what I'm dealing with here are a number of the bits and pieces that are supplemental. The textbook doesn't really get into the true stress, true strain. But if you start doing research elsewhere, if you start looking at other sources and they start talking about true stress or true strain, recognize that's a little bit different than the engineering stress and engineering strain over there. Now, there's a whole math behind this that we're not going to get into. but just I want you to recognize that it's out there. So as materials are selected, there are various things you want to look for, such as how much does it move when you apply a force to it, at what point is it going to break, at what point is it going to suddenly become plastically deformed. All right, questions to here?
So how would you calculate that?
Calculate this?
Yes. Cause you have cause that's the true strain of whatever the, elasticity of that, material. Cause each material is gonna be different.
Right, right. When you're talking about strain, you don't really talk about in terms of the strain of steel. It's not like, there's certain key points like yield strength and ultimate strength that you can deal with when dealing with a material. But strain really depends upon, you would not have, or at least I haven't seen anybody talking about, hey, here's this steel, here's the ultimate strain to it or anything like that. So in terms of calculating it,
Isn't strain just like the deformation of the object? So-
it's a measure of the how much it's deformed.
Right, so it just depends on what you're looking for, like
Right.
that's why there's like no set strain. Right?
Right, yes, exactly. Now, was your question around measuring strain in general, or true strain, or?
Yeah, I mean, cause you have, strain is just a deformity
Right.
of the material.
Yes.
And if you look at it, it might be minute or it might be large.
True. I feel like
And like, for example, if I went to a store and I'm looking for material and you wanna calculate, is this gonna be good enough for building a certain object?
Okay.
And you're gonna have to take in how much stress it's gonna take in a certain environment.
Right.
So how would you calculate looking at that?
All right, so it depends on, if you're keeping it in the elastic limit,
Yeah.
that's the easy one. If you know the Young's modulus of the material, and
So we have to use whatever the table.
right, you would use a table somewhere. So for example, I have one particular type of steel, the number for it right here, 6.89, so the Young's modulus is 6.89 times 10 to the 10th pascals. Or 68.9 gigapascals. And I know I am going to be, let's see, do I have a yield strength there? So let's make it something underneath that. I know I'm going to be applying let's make the math easy. Say we have a cross-sectional area of 1 square meter. This is a big thing that you're building. And we're going to be applying a stress to it, or a force to it, of 2 times 10 to the 9th newtons. So 1 square meter, so that's big. How much will it stretch? Well, first off, what is the stress that's going to be applied? I know the force, I know the cross-sectional area, so my stress should be force divided by area. I made the number so I could deal with it. So that's 2 times 10 to the 9th pascals.
Divided by.
And the next bit is, am I still in the elastic region? And based on this particular material, this has its yield strength, 2.16 times 10 to the 9 pascals. So the stress that I'm applying is less than the yield strength. So that means that I'm not going to worry about the plastic deformation, which means that I'm still in this region right here where they're directly proportional. So how much will it actually stretch? It's not going to stretch by plastic deformation, but it will stretch some, and it'll just go back to the original, or close enough to the original length. So I know that stress is equal to Young's modulus times the strain. And my stress is 2 times 10 to the 9th. And that's equal to my yield, my Young's modulus. Make sure I wrote that down right. Yeah, I did. 6.89 times 10 to the 10th. Yes, these are both pascals. Times my strain. The math problem is I have 2 times 10 to the 9th is equal to 6.89 times 10 to the 9th times my unknown. That's the math problem. So divide. Cancels out on this side, I'm left with just my strain. And over here,
Isn't it 6.8 times 10 to the 10?
it is, thank you. I wrote it down correctly right there, okay. And so this ends up being, whatever that is. Let's see, that would be somewhere around 0.03. Generally, just so you know, it's helpful in class if at least one person has a calculator, because oftentimes I will go, and that equals, hoping somebody will actually type it out. It's helpful if more than one person does it, just to, as a check.
Oh, yeah.
0.03,
0.29.
go that extra level. Getting the same thing?
No, I'm gonna do
0.029.
it. 6. Oh, I done the wrong player. 2. I have 0.29027 something.
You have 0.29?
0.029.
Okay. All right.
0.
And I assume, Selena, you got the same thing, or did you just stop?
I didn't, I just turned it on.
Okay,
I had it sitting over here, I didn't even have it on.
all right, so, well, anyway, let's assume that they both did it the same way and then that's the right answer. All right, so 0.029 is my strain. It doesn't tell us how much is actually stretched yet. What it does tell us is it stretched 2.9%. So we just need to know what that original length is. So Ronald's building a monument to his favorite person. So he's got this 1 square meter base here, and let's assume that the thing is 6 feet tall, 6 meters tall, just to keep metric. So how much does it actually stretch? Well, I know that 0.029 is equal to how much it actually stretched divided by the original length, which is change in length divided by 6. And so how much it actually stretches, 0.029 times 6 meters.
So it's 1.74 meters. Or, sorry, excuse me, 0.174 meters.
Okay. So he has a 6-foot monument, or stuck in the wrong era there. We have a 6 meter tall monument, and it stretches 17 centimeters. Now the question is that acceptable? If it is, great. If it's not, you are changing something. Either getting a different material so it doesn't stretch as much, or you are putting in some safety mechanism so the force never gets to be that much, or more specifically, so the stress does not get to be that much. Whatever seems appropriate for the design job. Did that even come close to answering your question?
Yeah, I just wanted to see how a problem would work out.
Okay. Questions to hear? All right. So if you pull on those plastic rings, there are two things that happen to the shape. And hopefully this does not evolve into a read my mind exercise. What are the two physical changes to it as you pull on it?
It gets thinner and it gets longer.
So that relationship between how long it gets and how thin it gets is captured in a number known as Poisson's ratio. The two numbers that are the two symbols that I have seen with it are the nu. It is not a V, it's a nu. It's like a V caught in a strong wind. And I've also seen, I'll put this parenthetically, sigma also used for Poisson's ratio. I do not want to use that because we're obviously using that for stress.
I bet that gets confusing.
There are so many things along the notation. Nu is also used for frequency. So, well, I'll talk about that later, but the nu and the V look very similar to each other depending on what font you're using. And in some fonts, a V looks like the nu in a different font. So it is defined by transverse strain divided by the longitudinal strain with a negative in front. Because one gets thinner, so that would be a negative strain. The longitudinal, so if I'm pulling on it, the longitudinal strain is positive because it's getting longer. The transverse strain is getting smaller, and they in general wanted Poisson's ratio to be a negative number. And so let's just run through an example. I'm going to use the numbers that I was using before. So I erased some of it, so let me rewrite some of it. So this is AER met steel. So there's a number in there. I really don't know what this is, other than it's a steel, it's some sort of relationship between carbon and iron. But this is the one that's what they had labeled for the specs. Different iron content, different percentage that's iron, different percentage that's carbon, how brittle it is, etc. There's a lot of different factors going into what type of steel that would actually be used. We have Young's modulus, was the one that I'd written up before. That's the 6.89 times 10 to the 10th pascals. Yield strength. .16 times 10 to the 9th pascals. Ultimate strength. .43 times 10 to the 9th pascals. So not too far off of this one. This steel is a little bit more brittle than a number of other ones. What I want us to assume, and this is not a valid assumption for the steel, but just in terms of working through a problem, assume that the volume of the steel stays constant. Within the elastic region. In reality, you're going to have the molecules that are holding each other together, and the way that they are bound to each other is going to change, and so the volume is not going to stay constant in reality. However, we will work with that assumption. And what I want to know is, what is Poisson's ratio if this is true? All right, so give some, so this is the specs for that particular material. So in this particular problem, we have that the length, the original length, is 10